this arithmetic Riemann-Roch and geometry of Riemann surfaces. So we start with something elementary. So you start with a compact Riemann surface of genus G, and you consider a punctured Riemann surface M0 in M. With M punctures. So you assume that 2G minus 2 plus N is strictly positive. Then by the uniformization theorem, what you get is that you can find a universal covering from up half space to M0. So in other words, you can find a function group of first type inside the BSL2R such that M0 becomes a standard quotient of the up half space. Of course, you can have a very natural compactification. Here is M. There you just add with those cusps. You can extend this map to pi bar on M. So the good thing about this one is that then on this up half space, you have this Bengali metric. This on up half space, by the invariance of this metric, you can get to the hyperbolic metric on M0. So this is the thing you can say about this open Riemann surface. And you can consider this one globally. You let this one to be a moduli space of punctured Riemann surface. M0, in other words, genus G with this N punctures. You will have a very natural Dunning-Mumford compactification. It's a stable compactification. So from this construction, what you can get is that you have a natural map from CGN to this guy is called universal curve. Of course, actually this one extends to MGN bar. We call this as M bar, sometimes just use pi bar or pi. And the good thing about this construction is that, of course, you have so-called the sections pi, I from 1, 2 to n. Each of this element contains M naught of P, actually M, P1, P2 to Pn. This equivalence class we send to just the Pi. You know the fiber of this guy will be just M. So then the sections we send the Pi, we send to just Pi. We will not distinguish between the sections or the image of the sections, which is a divider on this universal curve, or you can just say this is a line bundle, OCGN bar for this Pi, which is the line bundle corresponding to the image of this section. We will not make any distinction between any of this. And one of the property we need to use is that pi bar actually is flat. Of course, it's a relative dimension 1. And this flatness is going to be useful when we define refining this section called the linear pairing. So as you can see, because of this M and those punctures, classically you have two types of deformations. Associated with this punctured Riemann surface. One is, of course, the complex structure. The other will be the punctures. And in terms of spectrum theory, we know actually the complex structures, at least for compact case. In other words, without punctures, you know this deformation of this complex structures is measured by so-called discrete spectrum. Of the Laplacian. And the punctures, where all the problems come, you measure that one by using so-called Eisenstein series. This is so-called continuous spectrum. And in terms of the geometry of the global geometry of the moduli space, and the first one we all know is given by so-called we appear the metric on the moduli space, MGN. And all these things are on the open part. And in the end of, about the end of the 80s, and with the work of Takadaja and Zograf about this so-called locally family index theorem for these punctured Riemann surfaces, they introduced a very nice new metric on this modular space by using Eisenstein series. And that is the Takarajan-Zograf metric. This one actually, as what we said, is defined by using Eisenstein series. Somehow reflects the information coming from the punctures. And in terms of history, actually, and Wee-Peterson metric was first understood by using so-called the Aquila metric. In other words, people believe that this guy is cohomological. And even at that moment, there was a very beautiful result due to Wolpert. Yesterday, Kunio introduced this one. Actually, it's omega of square. If you take the you take the integration on the universal curve. Fiber-wise, you get from this hyperbolic metric, you get this hyperbolic volume form, 1-1 form, for the associated with the canonical line bundle. You take that 1-1 form, you wedge it with itself, you get a 2-2 form. You take integration, relative dimension 1, you get a 1-1 form. And this guy will be pi square of omega Weir-Peterson. Actually, this is a very basic result of Wolpert. And that already says that even though people didn't really understand at that moment, this is not really cohomological but intersectional. The Weir-Peterson metric essentially is in the style of intersection, not in the style of spectrum theory. But only because when, actually, of course, for Wolpert, he did this one for n equals 0, but that one can be generalized later on to for punctual Riemann surfaces. So the reason for this complication is that for compact Riemann surfaces, and there is a Riemann-Roch theorem, which says that lambda 1 to the power 12 equals, in my terminology, will be the Weir-Peterson line bundle. So here, you know, because you have determinant metric associated with so-called the k pi of lambda, which is lambda 1. And for that one, you can have the Quillen metric. So if you do the C1 of that one, then you basically get the Weir-Peterson. That's the reason why you at the beginning, well, people believe that actually this is somehow related with this Laplacian, the discrete spectrums. But of course, when punctures emerged, then you will get certain difficulties for this cohomological understanding. The essential difficulty.
May I ask you what is omega is?
Omega is C1 of the canonical bundle with hyperbolic metric. So this is the 1-1 form on CGN. The CG, yeah. So you have this one. In other words, it's just this canonical line bundle for this morphism, So when you have punctures, then as we said, from spectral point of view, you have the continuous spectrum. Then the very powerful method of Quillen, the Quillen's formalism cannot be applied. At least at that moment. Nowadays we have, in the audience we have the experts have done very beautiful result by partially overcome these difficulties. Now you have certain kinds of Quillen metric for special type of singular metrics. So today, I will use another method to solve this problem, but actually this one is independent of this Quillen metric approach. Even now, I cannot understand in general how can we do this by introduce this along with Quillen's line. So now the approach actually is not a cohomological one. So I'm not going to start with the determinant metric. I'll start with intersection. So refined intersection was initiated by Delin. So we call this one as Delin pairing. So I will not give you the general definition, but I will use example to illustrate this one. So you consider a surface, complex surface, dimension 2 thing. S here, you have two curves. One is C1, the other is C2. Then you know intersect at P1, P2, and P3. You have C1 close with C2 will be 3. That's the standard intersection theory. And then you say that maybe this is not good. What about if I say C1 with C2 equals P1 plus P2 plus P3? And actually, this is not a good definition. The reason is because this guy is zero cycle. So you have difficulties by doing the intersection purely on S using this language. And what Deligne tried to do is that, well, even though this is not good, but if I have a relative case, I have a curve, I have a fibration of curves, S over dimension 1. Then I will get Q1, Q2, Q3 on this curve B. Now this is very good. The reason is because I can define C1. I can generalize this as follows. So I have C1 and C2. So I will get two line bundles, OS of C1 of OS of C2. If I do this intersection with respect to this pi, then I will get a divisor, Q1 plus Q2 plus Q3 on B. That will give you a line bundle. Such that not only we have this at the level of line bundles, but I have this canonical section, O of SC1, 1 of C1. That's the vanishing divisor gives you C1 for this line bundle, 1 of C2. If I do the pairing, in other words, I can introduce a canonical section for this one. That one will give you just a canonical section of Q1 plus Q2 plus Q3. So in this sense, then we can refine the classical intersection theory for this relative dimension 1 case. So more generally, of course, I assume this is flat. More generally, the linear pairing gives you what? More generally, if I have a map from X to Y, which is a relative dimension n, for example. So I need line bundles L0, L1 to Ln, n plus 1 line bundles on X. Then by using the linear pairing formalism, I can get one line bundle on Y. Of course, if this one is metrized, is a line bundle with metric, then at least for smooth case, for smooth metric, in Deligne's work, he also offered us a canonical Deligne metric on this Deligne pairing, so that you, for two pairs, for a pair of for a pair of Hermitian line bundles on S, you can get a metrized line bundle on B. Similarly, you can do this metrized version. Then, of course, you want to know what happens if the metric is singular. There are certain difficulties for this one. So I will talk about this one later. But I will give you some definition by using this construction. Now I have this universal curve, CGN bar over this CGN. This is relative dimension. One relative is flat. So I need two line bundles here in order to get one line bundle there. So let me see what are the natural line bundles on CG m bar. So the first one natural line bundles on CG m bar. Of course, you have this k pi. This is a relative canonical line bundle, right? You get this one. And you get those sections. PIs, right? So actually, there is another one, which is a sort of related to this. What is this? We say that on each of the fiber of this M naught, there is a hyperbolic metric. If we consider hyperbolic metric as a metric on the compactified Riemann surface M, then a natural way to see this metric is you don't consider the relative tangent bundle, but consider so-called the logarithmic relative tangent bundle. So in other words, you consider k pi of P1 plus P2 plus Pn. You take its dual. So you have those are from algebraic structure, and those from the metric. Once you have these three, then you can introduce the following I think I will use this one. I will leave this here. Set of line bundles on your moduli space, MGN. There are two groups. One group is given by the intersection by using the linear pairing, group A. The first one I call this as the Weyl-Peterson line bundle. So delta of Weyl-Peterson is defined to be a k pi of P1 plus Pn. I do the linear pairing with itself. For this universal curve, Of course, I can take the dual here. I mean, double dual gives back to itself. So you essentially just consider logarithmic canonical line bundle. So this is Weyl-Peterson. Then you have Takdasian-Zuboff. Line bundle. For each I, you just consider k pi with this pi, right? That will give you n line bundles on MGN, and of course you have the total one, which is I use the additive notion. So this is the first group by using intersection. And you can have the second group by using the cohomology. So what happens is that I said that you have this k pi of P1 plus Pn. You do its dual. That will give you something natural associated with a hyperbolic metric. So then you tensor with minus m's power for m negative. Okay, in other words, you tensor with repeat minus m times. Then you take the Grudnik Mumford determinate line bundle, which Kunio yesterday recalled. And you call this one as lambda m, when m is less than 0. And when m is positive, and you consider k pi to the power 10 to the power m, then m minus 1 P1 plus m minus 1 Pn. You get a line bundle on CGN. You use Grudnik's Mumford's determinant formalism. You get a lambda bundle on MGN. So that is the case when M is positive. Particularly if you consider lambda 1, for example. If you consider lambda 1, what happens is that you essentially consider lambda for k pi. You don't do anything. Those punctures disappeared. And actually, this will be crucial when we introduce this determinant metric by using intersection theory. Okay, so those are the basic line bundles you can get on MGN bar. That actually controls the geometry of this moduli space of punctual Riemann surfaces. Then I would like to expose some of the fundamental relations among those bundles. Actually, there are 3 parts. This is an algebraic side. Later on, I will give you this analytic side. Finally, give you the geometric side. So, Zeno's 1 will be the duality. For the cohomologies, you have duality. And it reflects to this lambda m, the duality becomes this one. You can have the canonical isomorphism between lambda m and the lambda 1 of m. Because of this one, from now on, we will assume that m is bigger or equal to 1. And the first relation, then you have this logarithmic Mumford. Mumford did this one when n equals 0. Then we can see this structure in general. This actually is a kind of Riemann-Roch theorem. You have this lambda m. Of course, now m is a natural number. Tensor to the power 12th power, you have a canonical isomorphism to Weir-Peterson to the power 6m squared minus 6m plus 1. And mysteriously, you have pz and actually minus 1. And then I didn't mention between this MGM bar and MGN, there is a boundary divisor. This is a part of this Deligne-Mumford compactification theory. You get a normal closing divisor at infinity. So that is the data of the boundary. So we have this fundamental relation. And you can also compare this Weir-Peterson line bundle and Takladian-Zuboff line bundle. And the comparison between Takladian-Zuboff and Weir-Peterson. And this is given by this bundle. If you raise to the power n squared, that will give you tz. You raise to the power 2g minus 2 plus n squared. And actually, this will give you, and the sign for this one means that the difference takes intersection with the curve only on the open part of the MGN bar. In other words, MGN, the curve in MGN, most of the part, you take intersection with that difference will be positive. So actually this FR2 is quite deep. You see, there is a book by Harris and Morrison called Moduli of Curves. In that book, they ask several questions about moduli spaces. Then they state a result called basic inequality.